inches. 60% of 0.2 square inches is 0.12. You multiply that with a 300, 350 KSI. So you are talking about 350 times 0.12, whatever that thing. Then add that to the 40% of the other, you get a reasonable value, but that's not the way you look at it. There are other issues associated with it, but you can get within 15-20%. Instead, I would much prefer to talk about it, but the strain point of view. But the problem with the strain point of view is that I gave you 20,000 number based on 60% volume. If it is 40% volume, the strain number goes up. You see, so there are issues like that. Therefore, computationally, stiffness computation corresponding accuracy is superior to strength computation and the accuracy. And within the parentheses, you see the standard deviation. Very low. I mean, for a composite, we consider that 4.6% or whatever is reasonably low. And in some scenarios, it is even 1% to 2%, you know. Okay. So you can see both the flexural properties and here I'm focusing on the type of support. I can have it on knife edge like the one on left, and I can also have it on the roller, means that has a certain amount of contact area at the support. And it does make some small amount of difference. What is the issue there? Stress concentration is the issue. Yes. So anyway, keep some of that in mind. I think the ASTM thing calls for the right one, not the left one. So we went through all this in terms of tension properties, bending properties, shear properties, and so on. So you can see how the ribbed bars performed as opposed to sand-coated bars. One thing I want to point out, this may be a time to before we stop for, it's 1:30, stop for lunch. I would like to emphasize while we are talking about it is very, very, very important. When you run a test, please keep in mind the span length divided by the diameter ratio, that ratio. If L over D, span divided by diameter, is, again, the numbers I'm going to give you are not exact, but they're very close. I'm going to give you 4 numbers. If L over D ratio is higher than 35, 40, in that range, under a 3-point bending, you know what you're going to get? You are going to get a second-order nonlinear effects. So we never want to get there. This is the P delta effect, we call it. I don't know what you call it. It's a second-order effect. If L over D goes beyond 40, 38, 39, 40, in that range. If, on the other hand, if you want to have bending-based results, L over D should be hovering around 20 to 24. It could be 28, it could be 16 or 15, but it should be in that range for bending properties of the bar that I was talking about. There we go. What is the third? The third range of L over D is somewhere between 6 and 12. What does that kind of a failure mode give you? Shear.
Yes.
Okay. If you go below 6, you know what you're going to get? Local compression. Local compression. So keep those 4 in mind. Never ever conduct a test for bending below 12, above 40. To keep it somewhere in the mid zone, 20 to 24, or else your results can be skewed. That is the point. Okay, it's 1:30. I think time for you all to have a break. Then we will come back.
Yeah, sure. Thank you. Sorry, I have to go in between. I had a class. So.
I just want to show you this slide to highlight a point, that is, except that sand-coated bar for stiffness, but this is the same bar that we tested, same batch we tested, except that you can see how well the sand-coated ones seem to be correlating in relation to ribbed bars. So there is a greater uniformity, lower standard deviation with sand-coated bar than with the ribbed bar. So we have noticed that time and again. That's the point I just wanted to make it. And again, I want to repeat myself. I want you to keep in mind, if you exceed L over D ratio, 3840, you're going to get a nonlinear response. Your d square y over dx square is equal to mx over ei. You remember that? Good. Where is the nonlinearity coming there? It is good. The nonlinearity comes, this is what we call it, geometrically nonlinear response. You know the equation, d square y dx square is equal to mx over ei. So on the left side, you have really another term, a product term, which is 1 plus dy over dx whole square to the power 3/2. I don't know, you remember all that? Can I write it? Okay. I'm not used to writing this. I'm sorry, I'm not used to writing like this. So anyway, you remember that equation, right? So it is this term that is going to give you the nonlinearity part of it. So we are saying this is equal to 1, for example, I'm sorry, either 0, 1, that type of thing, depending upon the rate at which the deflection function is going to modify with respect to x. I don't know how much. So what happens here is that we are assuming 1 plus dy over dx whole square is 1 to make it a linear response. So this is what is called a second order linear, not linear, second order regular differential equation. The minute I multiply with this, it becomes, of course, a second order nonlinear differential equation. This is really not a nonlinear equation per se as we deal with it. We call it a quasi-linear equation, meaning that I can make it linear equation by some kind of mathematical substitution, whatever. Anyway, that's separate topic. What the topic here is, if L over D is, again, my numbers are approximate numbers in that range. I told you 100 times, I'll tell you 100 more times, just a range for a designer. If this is the case, then what happens? This y, when I apply 2p, for p I got y. When I apply 2p, will I get 2y? No. That's where the nonlinearity comes into picture. So we are not dealing with in that range. What we are dealing with is, say, this is the bending failure range. Again, please don't hold me for these extreme numbers. I don't know exactly, they could switch, and I already told you that. But a typical number, L over D, you want to test, if you want to have a bending failure, somewhere around 16 to 24, that's a good, so this is geometrically, I cannot write with this, nonlinear. This is bending. And then if it is this is shear. Compression, local. That is what one needs to keep in mind. So the P delta effect is not directly proportional once you go beyond 35, 40 type range. That's the message. So, yeah, the 6, L over D, 12, this is the shear failure. You know what a difference between, maybe this is a good time to introduce, you know the difference between a bending failure and a shear failure and a compression failure?
Yes.
Okay, good. Okay. So again, you can see by and large, we have had a better correlation with the sand coated by and large. I'm not, so the one I showed you, one or two are exceptions. I believe they may be bad samples. So here are some of the flexural properties. You can see the numbers for number 3 bar, say 145. Please look at how the strength to failure is decreasing with the increase in the bar size. It went from number 3, 145 to 128 to number 4 down to 117 to number 5. Okay, so that gives you an idea. And again, we can adjust the strengths as we want depending upon the magnitude of the volume percentage. I already explained what is how we conduct ASTM type testing for bending versus shear. I already did that. Here are some of the numbers. I'll tell you what is the difference between a single shear and a double shear in a minute. Go ahead.
So the percentage significance was that standard deviation?
You mean in the parentheses?
Yes,
Oh, that is the standard deviation. You know how to compute standard deviation, right? Yeah, that's what that is. So typically we had a fairly low degree of, low degree of standard deviation. As you can see, we tolerate 6 to 8, 5% is low, except I don't know what has happened to that one. That's relatively high. There may be, you see that would, you got a standard deviation of 15, 16, 18. You know what? That would immediately tell me something wrong with the way I'm conducting the experiment. Actually, you can see how nice the standard deviation is with regards to double shear. Okay, what's the difference between a single shear and a double shear? Do you know? So here we are talking about 4-point bending like thing as opposed to a 3-point bending like thing. That is with reference to the interlaminar shear. In terms of in-plane shear, the single shear, double shears are different. Okay, so here what we meant is that, so what is the difference between double shear and single shear computations? When you talk about a double shear, the central zone as zero bending, pure bending. When you deal with a single shear, it's a 3-point bending, and I'm beginning to see, we didn't pay much attention, now I'm paying. You know what? Why I believe we got such a variation? Because a very, very important point for you to recognize when you deal with composites, that is, we have influence on deformation from the standpoint of bending as well as shear. Okay, wait. That's a broad statement. The shear I'm talking about is Timoshenko shear. I'm assuming you know some of that. I can write an equation in a minute. So, say I have a bending stress, and bending stress means MC over I. Correspondingly, I have a deflection, PL cube over 4080I, that kind of a thing. Okay, that's one part. Then correspondingly, I also have a shear stress and a shear deformation. So, for metals, it does not matter a whole lot in the sense that the contribution of the shear in terms of deformation is about, say, 3%, 4%, assuming you follow my rules there. That is for metals. For composite, that contribution of deformation from shear is much higher. See, as he was pointing out, these two correspond to, I said, double shear, means there is a zero shear zone, therefore there is zero moment zone, therefore there is no shear type effect or influence as much as you have with the single shear. That is what caused it. So in a double shear, let me make myself clear, in a double shear, there's zero shear, constant bending. That's in a double shear, if you draw the deflected shear and the shear bending diagrams. In a single shear, there is no zero shear zone. Therefore, that no shear zone is contributing towards, that is, higher deflection. So, if you don't know about, this is a very, very important point. I chair the ASTM on the full-size component for composite. So we are planning to modify even the ASTM guidelines on that. So the important message is double shear, single shear, where you have nearly zero influence or less than 3-4% influence is with metals from the shear, whereas two of my students did work on shear influence on composites. The shear influence is about 10 to 16% depending upon the shear span. The shear span is A over D. I suppose you all know that. So that's the message I want to provide you with. Is that clear to you, all of you? Bond properties. How do we define bond? Why do we need bond? Let's start with that. Then we can see how to conduct a test for bond. A bond is the pull-out force from in a concrete environment. If you are talking about a pull-out force, if you take a cylinder, embed a bar and pull it out, right? That's what one way to do it. And how do you find the bond stress? Common sense tells you right off the bat, what am I going to do? Whatever the force I get by pulling out that bar, you see, this is the concrete environment. Here is the bar. I put special grip. I'm going to pull it out at that point while this is in a fixed platen. So immediately I say my force divided by the contact, pi d times the length, right?
Yes,
Okay.
stress, tau weight.
Yeah. Or the bond is force divided by the area, pi d times the embedded length, right? That's what common sense. Dead wrong. Why? Two reasons. At least two, maybe more. Number one, when the force is getting transmitted from the bar to the concrete, that stress is much, much higher at the entrance than the stress at the end. It's a parabolic distribution. You understand what I said?
Generally, we assume uniform.
It is not a uniform stress, whereas when you say the load divided by the perimeter times the length, that is uniform assumption. Exactly. Do you understand what I said?
Yes, sir.
Okay, that's one. I'm not implying you all go implement it, but at least you should be aware. The second most important reason why this quote-unquote uniform is not quite accurate, because in reality, when you do a beam bending type test to understand the bond, that beam has a bending component in addition to an axial component. We are not accounting for the bending component here because this is a pure axial.
Yes, sir.
You understand? So we had to construct an elaborate apparatus to simulate the bending effect. You don't have to know all that. As long as you appreciate, hey, in reality, when I'm dealing with the bond, I am going to keep in mind that this is not only a pull-out effect, but also a bending effect associated with it. Flexural bonding. Right. But it's so difficult to do that test. So people resort to it. You know what they do? They will reduce it by 10% or 15% or whatever. Suppose this gives me 2,500, I'll reduce it by 15%, that is 375, and 2125 is my bond. That's how, which is okay. Nothing. Again, remember, that's a designer approach. That's how a designer would do. Do you understand now what? Okay. Another extremely important item. Very, very important. Again, that's ASTM based. When we talk about the grip length, I know some of you may do it, some of the manufacturers may want to do it. The grip length as per ASTM must be 40 times the bar diameter. If I have a half-inch diameter bar, I better have the length to be 20 inches. If I have a 1-inch diameter bar, I better have 40 inches. Why? Because if I don't have that length, I will not be able to have the frictional force transfer from the grips of the machine to the grips of the bar. You get it? So the ASTM calls for, again, when I say 40, maybe 42, 38, it really doesn't matter, but it has to be in that range. And in that regard, a very important point is that if I do not create adequate compression of the grips in the perpendicular direction to the length of the grip, it would slip. And we in the US, I don't know what you all do, I think it's available here, we use a plyo grip, which is, I don't have any stock in plyo grip, let me assure you, but we use, and it works very nicely as a gripping, bonding chemical. It doesn't slip. Of course, it's a little bit painful. You have to go through a lot of stringent approaches of applying the material. That's the key. Remember, I'll give you a lot of thumb rules. The whole design is a thumb rule, right? Very few fundamental concepts apply of your mechanic. Most of the rest is a thumb rule. The thumb rule is whenever you apply a glue type material for bonding purposes do not exceed the glue thickness beyond 120 mils, means 120 divided by 1000 inches. That's, I said do not exceed, I said. Preferably stay between 40 to 60 if you can. Or else, you know what happened? The failure will be in the glue line, not in the specimen. That's why. And you also get an optimal resistance to pull force when you have between this 40, 50, 60 mils, divide that by 1000. So if you can keep that, so whoever is going to run your shop should be made aware of these simple things, or else you get your results falling all over the map.
Sir, but our Indian standard code, this setup is entirely different. We have another, Indian standard code is there, and we have a spiral-like thing, and from that we are.
That's fine. I'm not going to contradict. I leave that to you all. But I mean, generally, they don't take the numbers as my message, but take the principles as my message. Okay? That's why I always say this can vary a bit here and a bit there. But what are we trying to counter here? That is, how best can I transfer the force? That's one. How am I going to minimize the slippage? That's number two. So, my goal, remember, my goal is to make sure that the failure is in the gauge length. That is my goal. What is the gauge length? From this point to this point, right? So that is my goal. Whether, okay, another one, we did this. In lieu of plyo grip type of a coating, we have bonded with, of course, we had steel grips, no doubt. Then we machined inside the half moon, and then we used sand and bonded it. It worked well. So, but that's not ASTM. I'm just making a, so, but you can improvise things as long as you make sure that the failure is at the right location. More often than not, in these scenarios, the failure is in the grips or very, very close to the grips. Why? Because of stress concentration. So that is what we are trying to diffuse. How best can we diffuse the stress concentration? Oh.
So, my
Go ahead.
question is, even in the tension test, we use the similar gauge, the grip's length. If the grip length is less, and even my failure is within the gauge length, will it be permitted?
Yes. As long as the failure is in the gauge length, it is permitted. Okay. Why are we, maybe I didn't explain it well. Why are we wanting to have a 40 times the diameter? That's, maybe I should have addressed.
Transfer, basically.
I'm talking about, why am I talking about this length to be 40 times? You know why? I didn't explain that, sorry. Because we want to minimize the bending effects. That is why. Well, sometimes these forces that I'm exerting in the grip from the through the Instron machine or NTS machine, this may not be collinear. If it is not collinear, it would create a slight amount of bending. and if it creates bending, that bending I'm trying to minimize based on my, look at my principle of L over D over 40. So the same kind of a thinking process goes into that. You see? So that bending effect, yes, it may be there, but much, much less. That's why. So here are some of the bond properties. Sand coated and ribbed, and you can see sometimes the bond stress in the sand coated bars is, in our case, was higher, but in this case we have done, they gave us a big contract, we have done this work jointly, of course independently, in the sense the project was joint, testing was independent. So it's a kind of a blind test. They gave us 100 bars, somebody else, that is Florida Atlantic University, FAU. So we did that test. Anyway, you see the numbers. I have been telling you we got a bond, sand coated better bond values, but here it does not show that, yeah. So you can see other kinds of rebars. Please, in this bottom one, I want to highlight, if you look at the bottom one, what is a takeaway message from the bottom one? It has nothing to do with CFRP or GFRP. Yeah, there is some minor difference here and there, but essentially it is the bond effect between concrete and the bar. And I want to kind of highlight one more item. That is, make a comparison of this with steel. Steel, for the same bar diameter, etc., keeping that for the same concrete strength, same cover distance, steel is slightly lower by about 10% or so. So for our design purposes, we don't even say it is lower, right? It's in the ballpark range. That's how we will say it and leave it. See what I mean?
Yes. But on the steel surface, we have
lugs.
formations.
Oh yeah, lugs we call it. Yeah,
Yes.
yeah, oh yeah.
So comparatively, the sand coated, the size of that projection.
That is why you are getting a better bond, meaning you have a much higher contact area. That is what makes the bond better.
For that, we have to keep the gauge length in the range of 40 only.
Again, remember, why am I talking about 40? Where did the 40 come?
The bending.
The bending issue is what is making it a 40 number. I'm not saying, please, there'll be zero bending. I didn't say that. There may be some bending, but its influence is minimal.
To reduce the P delta effect, yes.
Huh?
To reduce the P delta effect.
That's right. Exactly right. So here you can see the sand coated versus the ribbed bar, some of the tests we did. You see here what I have been talking about with regards to the strength of the bond. Now people are asking how you're going to age the material, this and that. They want me to stop at 4 o'clock. I will stop at 3:30, 3:40, and then let you ask questions, okay? I mean, not only you, but people online, Okay, so here are what aging issues that we have done. So you can see very systematically, we did some with nanoclay, without nanoclay. That clay is Mont-Merilionite clay. And we have certain exfoliation problems when we mix with it. So you need to have a special mixture and all that. You know, otherwise you're going to get into intercalation issues, you know. So you can see that the ribbed versus sand-coated bars, how the moisture absorption is taking place in terms of the increase in weight over a number of days. These are kind of reflected in a broader sense in the knockdown factors. You remember what is a knockdown for moisture? What is a knockdown for pH value?
Yes.
So it all comes from this type of analysis. So here are some of the numbers that we did. So the ribbed bar and sand-coated bar. Moisture uptake in a sand-coated bar is, in this particular case, somewhat lower and stabilized quicker than in case of ribbed bars. Again, moisture getting entrapped below the helical wrap. That's what we call a ribbed bar, you see. So, but the message is you are getting about 0.15 to 0.25% increase over 300, about a year, you know, 320, 330 days. So where would the moisture go? It goes nowhere except entrapped in the thing, which increases the diameter, which is equivalent to your typical corrosion issue of a steel bar. Equivalent to it. It's not corrosion, remember, but somewhat. Phenomena of how the concrete is going to behave is similar to that. That's the point. And of course, 0.15% effect is much, much less than 10% equivalent effect of steel due to corrosion. So keep all that in perspective. So what we are saying is the hygrothermal response of GFRP under different conditioning schemes is increase in moisture is less than 0.5% over a year. Moisture in many samples was under 0.3%. Wonderful. But the bugbear is alkali condition absorbed twice the moisture. It absorbed twice the moisture. Why? Because the ASR, alkali silica reaction, is taking place already when you look at the moisture absorption. So, now we are going to get into the chemistry of resin. This is why I keep telling you polyesters are not very good compared to vinyl esters. What we did, again, these are all experimental programs. What we did, we made bars with vinyl ester. We made bars with polyester by pultrusion, but we have done a compression molding on top of the bar with ribs using polyurethane to minimize. That's cheaper process than the vinyl. Vinyl esters are approximately what? 2.5 times more expensive than polyesters. I don't know how much more here in this country. In our country, it's about $1.80 or so per pound for vinyl ester, 75 cents or so for polyester, maybe 80 cents. So, but that's what we did. So the message is, if you think vinyl ester is too expensive, use polyester. But you need to protect that bar with a compression molding using polyurethane type. Again, I have all that nitty-gritty information in this 300-page report. Somebody, when I go back home, I can send that report, you know. All that info is there. And including how we have conducted the Arrhenius equation. There you have the degradation rates of bars as well as the bars in concrete for 3 to 5 years. So here we go. It's already talking about the aging effects in relation to salt water. You can see that unaged water, 3% salt water, and sometimes the numbers may go up. That is due to post-curing. Keep that in mind, okay? Because when we pull through the bar, it may be cured 80, 85% or whatever that number, somewhere around plus minus 80%. I still have few ways to go to reach my 98%, 99% thing. So that comes with the aging of the material. Under normal environment, we want to put it in an autoclave, that curing goes faster. You can attain 98, 99% faster if you put it in an autoclave, but that's expensive. We also did work, as you can see, as I indicated, with the freeze thaw temperatures going from 12 to 120. Okay. F, we also did up to 180, 190. I didn't show that here. But this, again, repeating myself, the stiffness component is more stable than the strength component. So here you can see salt water room temperature, alkali conditions at room temperature for different months. So what we are showing is up to 30 months. And you can see that under alkali condition, with the far right bar diagram, what is it telling us? I lost about 32% of this strength. So that again is all in line with what happens under alkali silica reactions and what have you. No matter what, the alkali silica reactions have influence, and salt has less effect than alkalis. Both have effect, but one is slightly less effect, less damage. Here is the SEM, scanning electron microscope, that tells you, if you know how to read a SEM chart, you know what that means. So we did that work as well. See, GFRP bar after 9 months of aging under one. This is what is called accelerated aging test. So what do these mean? We put it all together at a later date and tell you the age of survival of the bar at different strength levels. Again, stiffness is not a primary issue because it doesn't get as much affected. If you look at the code, I'll talk about it, 15%, actually we only suggested a 5% reduction in stiffness, 15% reduction in strength. So now we are really getting into the code. The code, the ACI 44022, that's what I wrote there. ACI 44011. 440 is for FRP, 318 is for steel, reinforced concrete. 440 is FRP, reinforced concrete. We did not have a code, remember, we have a guide spec till 2022. This was approved. The things I'm going to be talking further and further are the ones that were approved in 2022. Okay. So the code has a repetition in the sense that they give you broad outlines first, then they get into very, very specific items after chapter number 10. It has 27 chapters or something. Some chapters are blank, remember, but whatever they could fill with a experimental confirmation, they did. One thing I want to tell you, somebody was asking me during lunch hour, you can violate the code, you can deviate from the code, provided you can justify why you're deviating. You follow me?
Sir.
Code clearly states at many locations that if you want to follow a cookbook approach, just follow the code. On the other hand, if you think you are going to challenge the code, challenge it. We don't mind it. We are not ashamed about it, because we learn from it. No, if you're going to tell me, no, my FRP bar is taking 300 KSI, wonderful. Show me that. That's all it is to it. All codes say that. It's not just ACI code. When I wrote the ASE all composite code, we said the same thing. So keep that in mind. Somebody was asking me at the lunch hour, what happens if it is this or if it is that? Nothing happens as long as you prove it. If you don't know how to prove it, then stay with the code, then you don't lose your license. Legally, you will be safe. Even otherwise, you can be safe if you can prove it.
Even the codes standards are formed based on the research data.
Yeah. And we don't have a lot of data, that's why the empirical is one, but we are also silent on the other. Where we are clearly saying we don't have enough info, therefore we are not going to encourage you to design it for that purpose. See, I could have, for example, I'm not saying I will, I could have challenged the code in terms of the FRP's ability to take more load in the compression zone, but nobody challenged it and they got away with it, you see. But on the other hand, if you run the test, you're running the test, or somebody was running the test. If you run the test and say, okay, I got twice the effect beyond the concrete zone type stresses, and you prove it, show it, then they will accept it. We are dying looking for such kind of information, really. Frankly, I'd been to China many times. Frankly, they are the only ones doing some good fundamental work. We are not, because we just don't have money for these kinds of works. The R&D monies, research and development monies, you see. But they are finding it, how long they will find it. Canadians are doing excellent work in the concrete area. We pretty much gave up I am able to do, that's why I moved away, to be honest with you, I moved away from doing the concrete FRP to all composite because most of my work is defense related. You see, they have the R&D programs, so that's how we are surviving. All right, so the code is going to be talking about the loads and the load paths for different systems. Okay, I want to start from the bottom, not from the top. Diaphragms not addressed. What does that mean? What is a diaphragm anyway?
A layer.
It is a structural component that would help transfer load from one main component to the next main component, like a beam. I may have 3 beams like this. If they are independent, the response is one thing, but if they are connected with a perpendicular beam, the response is different. So that is what is called a diaphragm. That's one. I mean, we're talking about shear diaphragms for the walls, for example. The concept is same. The structural function is same, but that's a beam element, this is a slab element. That's the difference. Do you understand what a diaphragm now? We don't have enough data. Therefore, we skipped. We didn't want to. Frankly, we don't even have a whole lot of data on the joints either with FRP. So there is very little direction. They have some vague terminology when it comes to joints. The others are fairly, I call it fairly standard because a lot of people have done a lot of work. That's why I said I'll go from bottom up. We have a pretty good handle on floors, both the 1 and the 2 slab. I provided you, did you all get the whole package of 300 slides, or did you only get a portion of the slide?
All the slides that sent to all the parts.
Okay. So if you look at later version of my handout, like say going from, gave you 299 slides. Between 299 and 249, you see the 2-way slab design with a great degree of depth. Beams, joists, columns, and walls. I provided you about 14 examples in addition to the theoretical part, you know. And then the foundations, you know. I did not provide anything on joints because there was no definitive ruling on joints in the code. Okay, no. Above designs are in accordance with 44011, chapters 7 through 16. Accommodate volume change from shrinkage and temperature through minimum amount of FRP reinforcement. I'll define what that minimum amount is. There are, unlike the steel code, which is a 0.018 times AS type thing for temperature and shrinkage, this is a little bit more involved than that. I'll explain all that as we go through the theoretical part. I'll explain it again when we go through the design part. Another unknown, differential settlements are not included in the load combinations for building design. What's a differential settlement?
Unequal settlements.
Unequal, especially if you have subsidence type problems. I think the northern India has more subsidence along the Himalayan region than the southern India, where you do not have whole lot of underground minings, you know. So that is where, and also now because of drawing off so much of underground water, you're getting into the sinkhole problems too, you see. So that's where you get into differential settlement. And you can easily get into differential settlement if you are rehabilitating the ground, meaning you cut and fill, you get into a lot of, so you have to be very careful, you know.
Even if in earthquake also we are facing the problem.
Well, yes, that is true. We are not talking of that kind of differential settlement, no. What we are talking is with time. The differential settlement with time. So the one you're talking about is a dynamic response. Here it is more like a creep type. It's a time-dependent response. I already told you many times, in a casual manner, in a serious manner, FRP concrete members under categories B to F are not covered. Even category A is covered only as a pseudo-static response, not as a true dynamic response. So here, what I'm providing you as a note of caution, perhaps a disclaimer, all the following slides that I'm going to provide you are a summary of what is in the code. I'm not trying to replace the code. So, we are now in the thick of the presentations on design of GFRP in concrete. Even though I said C cap C sub E is a environmental reduction factor, for glass I said is 0.8, now they're using 0.85. Therefore, what I'm really trying to say by that statement is that last right column is a guide for you, and that last right column varies from one code to the other code. It varies from one type of structure to the other type of structure, from one country to the other. Therefore, even though I'm using those as a number, but you need to fill in an appropriate number depending upon the country you're using. Like you are saying you're using German code, somebody is using a Russian code. They may have, but by and large the numbers are about same, maybe 5% difference, but not vastly different.
So these reduction factors for how many years of life of structure?
We like to tell people 100 years. Again, like I said, I told you, kept telling you 350 page. We based on the accelerated aging data, based on very, very limited natural aging data, based on the theoretical information that is known as the Arrhenius response. Based on all that, we have arrived at this. You know, that does not mean we are right.
So, in your laboratory, you have done the aging testing.
Yes.
And also from 30 years back, you started working on GFRP, using GFRP in bridges.
Right.
So, have you ever relayed the
Yes.
experiments? And
Yes. Not only related, I got a big project approved to do more of that. I haven't started that yet. The monies didn't come in, but they approved it. I'm starting it next couple of months. Yes.
So, what were your observations from the experimental to the...
Stiffness wise, we are very accurate. I have some serious concerns from the strength side. I didn't win the battle on the strength side. I wanted to reduce that to more like 0.65.
From 0.85 to 0.65.
There are reasons, I don't want to get into the science part of it, but we have shown that under certain scenarios, it can be, not the stiffness, the strength. In summary, I gave you my answer. So we talked extensively about this. See right here, please note how dynamic it is. Here I said, okay, here I said 8.8, here I said 0.85. It used to be 0.8, changed to 0.85 come 2022. So that's how dynamic the change is. So all I'm saying is use caution, use common sense, and then use the right kind of a code for the right kind of a region, like north versus south, freezing versus thawing, these kinds of things. But the procedure is same. So there are two things I want to mention, highlight, and maybe talk extensively. I'll stop here because I would like to restart it in the morning. But before we start the Q&A session, what I want to say are the two very, very important. What is FFU? What is F star FU? Here is the answer. FFU is the design tensile strength considering reductions for service, environment, or whatever. Whereas, what is that?
Megapascal.
Yeah. Look at CE, the correction factor, multiplied by F star FU. What is F star FU? It is average value. So, really, by the time you come here, it is a 25% reduction in that range. Then when you go from here to here, another 20, 25. So really, my message is, when you run the design, you are operating around 40 to 50% of its average value. But, I'll show you some other thing. The real operating ranges are half of that or 1/3 of that. Meaning, if I have 100 units, I'm talking about 55 units is my FFU, okay? Yes. But I'm not operating at that level. I'm operating about 1/2 of that level. So 100 becomes 50, becomes 16 or 20, So which means what? I have a factor of safety of 5. They want me to keep the factor of safety around 7. So my ignorance of the product is buried into that factor of safety. So with that, I want to start because we are now getting into the most critical aspects of design, not the analysis, not the science part of it, but the design part of it. Therefore, we'll start afresh, but it's 3:30 exactly. I will take the Q&A for the next half hour.
The previous slides you showed nano clay with GFRP accelerated corrosion. What was it used? It was covering the bars, or it was used for covering the bars, or it was mixed with
the nano clay. The question he was asking me about nano clay. This is the scanning electron microscope results. Some are with nano clay, some are without. But my message is that the nano clay is no more than 10%, maybe a little bit less, 10, 12%. But
in the matrix.
In the matrix. Okay. And as I said, there are two kinds of nanomaterial we used. One is the nano clay, that's the montmorillonite. The other is carbon nanotubes.
As an additive.
As an additive in the resin. The toughest part of using a nanomaterial is exfoliation of the material. It's not easy. How do you exfoliate from the standpoint of clinkering of the material? How do you disperse the material? That is called exfoliation. Intercalation is bound material that needs to be exfoliated. So there are special machines to do. Again, okay, you can do all that in a small lab setting, but it gets very difficult to disperse it evenly on a high volume basis. If you don't disperse it, you're going to get into a bigger problem, much bigger problem, because a chain is as strong as its weak link, right? That's what happens if narrow clay is intercalated, then that is the weak link and it'll break right there.
So what are the changes which happens when we add these materials?
Two things. Stiffness increases because I'm replacing 10-12%. Resin stiffness is lower than that of the clay. Most important than stiffness increase, these are nominal. Permeability decreases. That is the key. It's the permeability issue that we are always struggling with. When we talk about a nanomaterial dispersion, we want to see how much of the permeability, meaning moisture ingress or ASR ingress, is what we are trying to minimize.
Even the voids percentage also will get reduced.
Now it doesn't matter a whole lot in the sense that I have a protective barrier of some kind and nothing, water doesn't get in, expand and contract like that.
But the thing is, the void percentage will influence the strength of the material.
Oh yeah, it does. So we have to be careful about it. That is why I said a intercalated nano clay, if it is not properly dispersed, exfoliated, gives me a bigger problem. That's why, yeah, you have to have a very uniform I didn't show here, I have a number of SEM plots where it is not dispersing well enough, then obviously that shows up in your results.
So in the more previous slides, there was some symbols used, A, U something, with the GFRP bars, with CFRP bars. In the previous slides, what were the symbols? More previous. In the previous slides.
We go forward or backward?
Backwards.
I'm going backwards.
Maybe that is
FAU, WVU.
Oh, that's a university name. See, we got a contract to do this independently by 2 or 3 places. We did it at 3 places. One is Sherbrooke, the other is Florida Atlantic University, and the third is WVU. Sherbrooke is in Canada.
And one more thing, sir. Like you were saying that the fatigue life of FRP reinforced members are more than that of steel reinforced members. Fatigue life. So how is that? But as we know that the stress strain curve of steel is the area and the stress strain curve of steel is more than that of FRP bars. So how we?
Okay. I am comparing up to the yield point. I'm not comparing the area under that beyond the initial formation of the plateau. Because when we are talking about the fatigue, we do not operate in the yield zone. We only operate, I don't know whether I can show you that, whether I have it here or not. Okay, we remember, I told you many times, we only operate in this zone in terms of actual load transfers and what have you. In reality, so when you have fatigue, that in steel, that comes down here. That is why we have a higher energy reserve with FRP.
Is it more because the crack opening is more the FRP members?
It should be worse if that is the case, you see. So I'll give you another way. I never said this, I should. I forgot really. Compatibility in terms of stiffness of FRP to concrete is fantastic. Why? They're all about 3 to 4, 5 MSI range. Whereas the steel is 6 times stiffer than concrete. 30 million is steel. Concrete is about recent concretes, not the old 4.5 million PSI. The high strength concretes are 5, 6. So that is a bad news because incompatible from the strain point of view. If both are acting in unison in terms of strain, it would behave better than otherwise. What happens is the steel gets debonded quicker than FRP. That's
Integrity is
yeah. The affinity is always the issue. Materials behave like humans, or humans behave like, when you talk of creep, I don't know, you use the expression or not, you say, you call a human being a creep, right? So what does that mean really? Where did the word come from, So it is stress that you create for yourself or beyond a point, then you crack. That's what it is. Okay.
One more thing, sir. When we apply cyclic loading on a FRP frame, for example, the thing is that in case of the steel reinforced member, there is formation of plastic hinges because
We don't have that.
we don't have that in FRP.
Correct.
So it means that we can't use that in seismic zones or.
Well, again, we don't have enough data to speak about that like the way you are saying. We are a little bit cautious, so I don't know how to really phrase it. Yeah.
You are saying that the energy dissipation is more in FRP members, but there is also that in the case of cyclic loading, it will not be able to recover from one space.
That depends on the compression failure or a tension failure. You have to look at that as well, right? You cannot only just look at it from the steel point of view. It's a combination of concrete and steel. That is where you get into the tension failure compression. I will show you, I hope I have it, how a stress strain curve under compression behaves vis-a-vis that under tension. Then you will appreciate it.
Sir, in the latter slides, in various environmental zones, like the alkaline exposure and all, what was the binding material there, sir, for the FRP bar?
The one we have been constantly, earlier we used polyester with polyurethane coating, right, that's earlier. Yes. But later on we have consistently used vinyl ester.
Vinyl ester is more resistant to the alkaline condition.
Exactly, absolutely, there's no question about it. Yes. You will see in this report, we did the polyester, did the accelerated testing, we did polyester with polyurethane coating or compression, then we did the vinyl ester. You can see how it is behaving.
So from a commercial point of view, you mentioned that you use PU resin to coat it. You use PU resin to coat it under compression molding, right? But it's not possible for a mass production line.
Okay. In US, we have what we call a continuous compression molding machine. So, on one hand, it is a batch process. On the other, once you make it continuous compression molding, and it becomes a continuous process. So we do have, I agree, what you said is correct, I'm not denying it, but if I can make it into a continuous compression molding, then I'm able to get a larger production run going.
You have in the US you have compression molding machines up to 6 meters.
Huh. We have a machine. I have one in my lab that is, what is 40 feet? 13 meters or 12 meters.
Yes, sir. Sir, and what about epoxy resins?
What about?
Epoxy resins.
Okay. Epoxies are the derivatives of vinyl ester. They're good. They're good. Very good. Except that we did not have epoxies of low viscosity till recently. That was our problem. But now we do. Typically, epoxies have a viscosity olden days, not now. 2000, 1500, whatever. Today we are getting epoxy that are 150, 200 centipoise.
People are using thermoplastic resins also.
We don't. We don't use thermoplastics for main rebars. Yes, we do use thermoplastic for stirrups. Yes, because that's easy to make and bend, but not for the main rebar. No.
So from the strength or stiffness point of view or durability?
Its molding becomes a bigger problem with thermoplastics. It's very difficult to get quote-unquote continuous manufacturing process with because these are pellets. I have to make this into some kind of a dough, and the doughs are what? 10, 15, 20,000 centipoise? That's from that standpoint. And I don't know how good they are in terms of environmental issues. And I do not know how the crack propagation of the bar itself. I don't know, I'm saying.
You were saying one thing that the data on compression tests are not available.
Repeat?
The data on column compression, axial compression.
Very few have done that so far. Yes, there are some small studies, like I said, the Chinese have done. He is trying to do some of that. But think about it for 1 minute. Even if I have a 6-inch by 6-inch column, what's that? That's about 36 square inches. I multiply that with 5,000 psi. I'm suddenly talking about I need a 200 kip machine. I have a 750 kip machine, okay? But I'm just saying 6 by 6 is nothing. How do you, when you scale it up to 12 by 12, that is 144 multiplied by 5, that's 750 kip loading. That is where it's falling apart. That's why we couldn't do, I mean, again, we can do, but it's very expensive.
Actually, sir, in lab testing, we use doing the compression testing. So we did in our lab, professor has also done, me and myself are also.
What size?
We did for different L by D. So I went for 10 by
10 by 10.
So that it can replicate the general.
No. What size column?
Oh,
About the column,
column.
not the rebar.
Okay, so in column.
Actually, I had struggled the same problem, sir. So I did 300 mm by 300 mm, that is 12 inch by 12 inch. Few samples I could not able to do because that went more than 3,000 kilonewtons.
There we go.
My capacity of the machine is only 3,000.
That's the problem.
So after I got 12,000 kilonewton machine, then I started doing it.
Even that, I say, is low. The reason is very simple. Nobody is going to accept your data if you say, I have done a 6-inch by 6-inch column or 8-inch by 8-inch column. You know why? The scale-up is an issue. How do you tell me whether that is a valid result, 18-inch by 18-inch column? So there it fell apart. So maybe...
Any other questions?
So at what load should the columns be tested?
At what?
At what load should the column be tested? Full scale columns.
No, you have to test it to failure.
Yes, okay.
That's what it is. If you don't test it to failure, there's no sense, because we know it's going to be a linear response up to a point, like say 45% or 50%, it's a linear response, maybe more being a compression. In a bending response, it's a linear up to 45% of the ultimate. But in a column, it may be linear up to 70%, because eventually you will never ever have a collinear force generation. If you don't have it, any slight amount of non-collinearity will bring you the bending. Then you are confused now, is it compression fully, or is it a combination of compression and bending? See?
So is the ASTM standards for testing of steel and FRP are same?
Repeat?
ASTM standards for testing steel and FRP same or different?
No, they're not. Okay, wait, they're not. Now, you have to define for me what testing are you talking about with regards to GFRP, meaning are we talking about all GFRP system or rebar, number one? Are we talking about bending, shear, whatever, compression is number two? Are we talking about static or dynamic? So some are beginning to be addressed. They're not fully addressed. As I said, I'm chairing the committee dealing with full-size sections. I don't know what the concrete guys are doing. I stepped out of that domain, you know.
One more.
Sure.
That here in the code ASTM you have not determined the strength for the joint, and definitely we require the strength of this joint for the connections. So for repair and maintenance purposes, we also require the. How do you follow that?
That is the issue, isn't it? That is why, you know, industry would love to get you to implement it in a much higher volume so they can make money, but we are not able to do it as a designer due to the lack of information. That is the difficulty with concrete. We made excellent headways with all composite systems. I have a 260 slide deck exclusively talking about joints, mechanical joints, forget about bonded joint, in composite. We did make it somewhat easier. These guys have a long ways to go, 10 years to go before they can even think. They can't even test a column, forget about a joint. You understand what I'm saying?
So are we getting a used point in testing the tensity test of FRP bars?
Oh, we have those. Very standard now. ASTM has that. Well, you can ask the ASTM. If you don't get it, since I'm a member or whatever they call it, writing member, they give it to me free.
So there are one or two questions are there from the online.
Sure.
So they would like to speak to you directly. So just,
Sir, do you think that it is possible to make FRP composite housing structure with just FRP bars? With only FRP bars? Means maybe at the joints it is important to incorporate laminates also.
That depends. Somebody can challenge it, but
And the columns can also not withstand so much compressive force.
that's what they want you to believe. That's what the code is making you believe that. I'm saying no. They take at least 2 to 3 times more load than a concrete does. I don't know where they got that argument.
So how can we make a column with FRP composites? Because FRP bar reinforced concrete will not take that much load.
Well, people like him in India should test it and establish for once that yes, they will take the 2 times, 3 times, 4 times larger as much as that of steel and move on. But they are not doing that. We cannot do it. They don't give us money. We don't have it. They're not allowing us that. Okay, go ahead.
Yeah, there is a question, sir. MS rebars are recyclable. What about FRP bars?
That's a good question. Very good question. We are beginning to recycle thermoset-based composites. We just started that operation. Okay, what does that mean? We call in a scientific field, we call that IPN, we call it IPN, interpenetrating polymer networking. In a broad sense, if you apply enough pressure, time, and heat, anything will degrade, right?
Sure.
As simple as we know that. So, how we control the time temperature with a catalyst is what we are doing. Therefore, it's not difficult to recycle, but what we are trying to do is upcycle it more than recycling it by adding a resin to a softened composite so that we would upscale it than downscaling it. Yes, it is not difficult. As we see today, I would have said it is difficult 5 years or 10 years ago. Maybe I'm saying that because I'm getting a patent on that one. Yeah.
Is it being done currently, sir? Recycling?
Yes.
So there is one more question. FRP rebars recycling is also in designer's scope?
Not right now. Not right now. Eventually, I think it will. You see, Europeans are much more alert about recycling. They have built all that into their cost-related issues. If you don't recycle, you're going to pay for it. Is that stringent in Europe, not in US. So that is why, I think if I remember right, come 2030 or something, don't quote me on the year, 90% of all the Germans, particularly car, body, 90% must be recyclable. You know what they're going to do? They're going to upfront make you pay, and then they'll give the money back provided it is 90% recyclable. That's how stringent they are. But not in US.
So recycling means where we can reuse it.
Where you use it, there are 2, 3, 4 venues. Like one venue I told you is you use this IPN, interpenetrating polymer networking concept, to upscale it. That's number one. I'll give you, since you asked the question, we are in the thick of it, I'll give you a better answer. Take the case of a windmill blade. I told you we are now discarding 120 feet long blade, 200 foot long blade, all that. We are more now into 300 foot long, like that. Okay. What they are doing is, for example, they will cut the blades and use as structural elements or playground elements or your, what do you call, the seashore, those walks they call it. What is that? The walking thing on this, things like that. That's why I use the word, the three words here, two. One is upscaling, then downscaling. So recycling can be upscaling with the IPN, interpenetrating polymer network, or it can be downscaling by simply a brute force method of cutting it and using it as some kind of a playground material or boardwalks. That's what I was looking. You know, you can make a boardwalk, right? With these big, yeah. Or decks. The backyard. That's not very prevalent in India, but in US it's very common. Single-family dwellings have a decking system at the back of the house, right? So it's very popular that. Go ahead.
So RMC also uses silica as the raw material when when concrete is being made, cement is being made. So would you recommend FRP being used, being recycled as a part of that in order to get silica component in it?
I can't answer. Now tell me, is that, you see, by burning it or doing whatever other kinds of thing, the problem is going to generate carcinogens. So you have to be careful there. Then you have to send it through a plume that would capture the carcinogens and this and that. So that's why I don't want to get into that type
because most of the industries in India are doing that. Like if they want to recycle their FRP channels or anything, they are sending it away to these RMC industries, and part of it is being used as an additive instead of silica. So,
ground it down to some level and then add it as an additive in lieu of your filler materials, conventional filler materials like calcium carbonate or something, that's acceptable. But burning it is not acceptable.
One more question, sir. Mm-hmm. Minimum size of the beam may be permitted for testing. What is the minimum size of the beam may be permitted for testing?
You mean in concrete?
How much we may reduce the size?
Okay. You mean in concrete?
In concrete, using FRP.
Typically, concrete people have been in it for a long time. 12 to 15 inches, 12 by 12 or 50, no more than 18 inches is considered as a reasonable. Number two, as a bare minimum thing, if you want to increase it for design purposes by a factor of 2 for the sizing effects, right word, sizer. Meaning, if I use 12 inches, probably they'll accept up to 24 inches.
Then what will be the length, sir? If we are considering 12 inches, the L by D ratio again 40.
L by D ratio, if you want to evaluate the bending failure, it must be around 24. 12 inches means you need a 24-foot long span, in that range, maybe 20-foot long span, if it is 12 inch. If it is 18-inch depth, again the L by D ratio should be around 20, 24. So you're talking about a 36 feet. Right. That ratio, maybe you can go down to 16, for example, to minimize this span. I want to use the word test span.
Again, it depends on whether we are doing for flexure or shear.
Yeah. That's what she's asking about bending, right? Yeah. Okay, very good. So this is about 4 o'clock, 4:02. We're right on time.